So let's talk about data. That's really where everything starts. So this is an example data set for a house price versus a house size. You may argue that a house price depends on more than just a house size, and I agree. But I would like to keep this simple to focus on the key concept. If we understand this key concept, it's applicable to all factors that a house price would depend on. So if you look at this set of data and ask the question, can we find a line that presents the best fit for this data? And the answer might be a line like this. The line goes through the origin at 0, and the equation for that line is y hat equals w1 times x1. It's y hat to distinguish it from the actual value. So let's just take this data point as an example. This data point has the coordinate y, which is the actual value for the house price for a given house size. However, the line has a different value for the house price because it's really an approximation for the house price. And the approximation from this line for this data point is y hat to really distinguish it from the actual value. But what if our data points are arranged in a way that the best fit line does not go through the origin? For example, like this. The best fit line for these data points might be like this. So there is a bias. This is the intercept when x is 0, when x1 is 0, y hat equals b. And that's called the bias or the intercept. But of course, the data points may not be arranged in a way that a best fit may be represented by a line like this. So a straight line may not be the best fit for these data points. So we really need to have the capability to come up with a best fit that is not a straight line. So we need to be able to cover the cases where a straight line is a best fit or a nonlinear fit, like what's presented in these data points. And of course, you can imagine as we add more coordinates, more features, like you have x2, x3, x4 in addition to x1, these data points are distributed in a very complex space that cannot be really visualized. We can visualize three-dimensional space, but beyond that, it's really impossible. So now to our key concept underlying all machine learning models. So basically, this is a representation, another way to present what I just shared with you. So we have the x1 variable, which is in our case, the house size as an example. There is a weight parameter, and there is the bias. The bias is nothing but x0 times w0. X0 is always 1, and w0 is the bias. This computational unit, all it's doing is taking the weight for x1, multiplying it by x1, and then add the bias to the result. This is also called the dot product. Dot product of two vectors. X1 also has a name feature. So no matter how many input variables, x1, x2, x3, all these are called features. X0 is always 1. And here is the simple math for the bias. This computational unit provide a simple output, which is really just the dot product, which is the predicted value for the house price. I started really with the perceptron in the inference phase, meaning the perceptron has these parameters already defined, predetermined after training, because training really needs to happen first to find the best fit for the data. Once that's done, we know what the bias is, we know what the weight is, and now the perceptron can actually provide a prediction for a specific input. So this is really quick, the dot product of two vectors. We have vector v0 that has these elements, w0, w1, and vector v1 has these elements, x0, x1. And we're going to talk later more about dot products. This is really a very simple case. To really do the dot product for these two vectors, we have to transpose vector v0, and we'll talk more about that in future videos. So, but here, the dot product for the two vectors simply equals to what the computational unit provides or doing. But this gave us the linear set as I presented you on the previous slide. But how can we get the nonlinear fit? If the data has a nonlinear fit, how can we do this here? We apply an activation function. Essentially, the linear results coming from this computational unit is input into an activation function, that will give us the nonlinear fit to the data. What's the activation function? We're going to talk a lot about that in the future videos. But for now, example activation functions include the sine function, ReLU function, sigmoid, etc. In machine learning literature, the input data is also called input layer. These computational units together are really the perceptron or the artificial neuron doing these computations. And when we have a lot of these perceptrons or artificial neurons working together, that would be a computing layer, and you may have multiple computing layers. As a matter of fact, that's the case for complex models. You typically have multiple computing layers. And then this is the output layer that has the prediction.